I think we can start now. So hello and welcome everybody to today's webinar. In this webinar, we welcome again Dr. Navneet Kumar from Center for Development Research in Bonn. I think we can keep the introduction short this time since we met you this morning. So maybe you can still give us a short introduction of yourself before starting with your presentation. Thank you.
Thanks, Anna. Hello, everybody. I am Navneet Kumar, working as a senior researcher at Center for Development Research in short ZEF, which is a part of University of Bonn in Germany. And I'm working on the issues of water management, hydrological modeling, climate change impacts, and also with the applications of different remote sensing and GIS technologies. Welcome to today's webinar on Earth observation and GIS technology for spatial management of water resources. So I structured this presentation in two parts. The first part is about the theoretical aspects of remote sensing and GIS and its application in water resource management. And the second part is about the practical insights of how to use remote sensing and GIS application for acquiring data for your study. So in the theoretical part, it is structured into three parts. First, I will talk about the basics of remote sensing and geographical information system. Then I will talk about how that remote sensing techniques can be useful for acquiring information about the different hydrological parameters. That is about evapotranspiration, soil moisture, etc. And at the end, I will talk about the different applications of remote sensing and GIS in water resource management. In the second part, that is a practical exercise, I will show you how to bulk download the rainfall estimated by remote sensing, how to download the satellite images, and also about the digital elevation model. I will also show you the flood monitoring tools that uses remote sensing observation for flood monitoring, and that can be useful for you to have a look on those websites. So let's start with the fundamentals of remote sensing and GIS. So what is remote sensing? You might have heard about remote sensing several times, but what is the definition of remote sensing? Remote sensing is basically an art and science of acquiring information about an object without being in touch with that object. That means it is a technique which can facilitate the acquisition of data from a certain distance without being in contact with that object. Remote sensing basically requires sensors and a platform for data acquisition. And it all depends on the type of application that we are going to apply. So with this definition, our human eye is also acts as a remote sensor because our eyes are installed on the skeleton and we can observe different objects from the distance. That is also a type of remote sensing. But basically, we are mainly interested when we talk about remote sensing is space-borne technology, that is the satellite remote sensing. So you can see that the platform could be a drone. Drone can also take information from a certain distance from Earth and provide information about the Earth object. It could be aeroplanes that are capturing information, or it can be also satellites which are space-borne in the space that is continuously capturing the information for our use. So we are basically, when we talk about remote sensing, we are basically interested about satellite remote sensing because that is providing us the data and continuous time scale. You can also see if we change the platform, if it is higher at a higher altitude, the level of information, the details of the information will decrease, but the spatial extent of the data acquisition will increase. So you see that it takes for the larger extent, but the amount of information that it captures will be comparatively less than what is captured by drones or by planes. So it all depends. So it depends on what information do we need, how much detail we need. If you need too much detail for a field scale study, it is recommended to go with the drones or aeroplanes. What type of detail we need, whether we are interested for flood monitoring or whether we are interested for forest monitoring, land use mapping, or what is the application and how frequently we need the data, means how fast we want to acquire the data, whether we need the data in daily time steps or we need the data at the monthly time step. So it all depends what is the need of our application. So why we need a remote sensing? Because with remote sensing, we can observe the objects better. If we observe the objects better, we understand it better. If we understand it better, we use it better. And if we use it better, our life will be better. So you can see that there are several advantages of satellite remote sensing. First, it provides data for a large area. It provides data for the whole globe, for the whole Earth. It provides data for the remote and inaccessible area. That is, it provides data from the top of a mountain to the middle of a sea or to the middle of a forest, where going to the places are quite different, then also difficult. Then also we can observe data without going to the places using remote sensing. Also, it provides information on daily or continuous time steps. At every time, it is providing information, and with this information, we get easy and rapid collection of data. So it is time and labor efficient technology. With the huge amount of data on a continuous basis, we have the possibility to produce maps for interpretation. And these maps are quite useful for the decision and policymakers. Now, how does it work? What is the process behind remote sensing? So you can see that the light energy is the basic principle behind remote sensing. It's an electromagnetic spectrum is the basic principle behind remote sensing. So you can see that the light, when it reaches the atmosphere, it is either absorbed, scattered, or reflected by the Earth's surface. And this reflected energy is captured by the satellite sensors. And this information about the object is then captured in the satellite sensors. That information is then sent to the ground station, and where it is processed, and with this processed data is then put on the server for further use. So we can download then the data from the servers where it is located, and then we use it for various applications. So you see that there are different processes when the light reaches Earth. Either it is reflected back to the sensor or it is absorbed. And later this absorbed light energy is also emitted as a thermal energy, and that is also captured by remote sensing sensors. So as I said, the basic principle behind remote sensing is the electromagnetic spectrum. You can see that the electromagnetic energy travels in waves and spans a broad spectrum from very short gamma rays to very long radio waves. Our human eyes has capability to see only in the small region of electromagnetic spectrum, that is visible light, between 400 to 700 nanometers. But an object can reflect differently in the different regions of electromagnetic radiation. And remote sensing is basically specialized to look beyond this visible region. So remote sensing can capture information in infrared region and microwave reason as well. So it provides a lot of information about an object which our human eyes are not able to detect. So you can see that it's operate in microwave region, visible region, and infrared region of the electromagnetic spectrum. Now, the concept of atmospheric windows. The atmospheric windows are part of electromagnetic spectrum that are transparent for specific wavelength. They allow the energy to pass through the atmosphere to Earth's surface and are favorable for remote sensing. So here I mean that the energy that is reflected back to the atmosphere towards the space is absorbed in the atmosphere, certain part of the electromagnetic spectrum, because of different gases available in the atmosphere, which is water vapor, carbon dioxide, and ozone. So these molecules, they absorb certain part of the electromagnetic radiation, and they allow certain part of electromagnetic radiation to pass through them. So if they are absorbed in this, they are not useful for remote sensing because the reflected rays are not reaching to the sensors in space. Whereas certain portion of the electromagnetic radiation are clear, are showing a clear window for remote sensing. They are allowing the light to pass through them. So you see that the visible region and part of ultraviolet region is good for remote sensing. You see also in the range of infrared spectrum, you will see that there are certain portions which are quite clear to remote sensing. And you can also see that a big portion of microwave region is very good for remote sensing because they are transparent to this spectrum range. So that's why if we can use this microwave or infrared region, we have good information about the Earth's surface. Now, as I said, light is the main source of remote sensing. So what are the sources of electromagnetic radiation used in remote sensing? So first is the star, suns and stars. The sun is the main source of energy that is used for remote sensing. Also, all bodies with temperature more than 300 Kelvin is also for remote sensing because they are the thermal infrared. They fall in the thermal infrared spectrum of electromagnetic radiation. Also, microwave region is good, and the lasers that produce energy is useful for remote sensing. So based on that, there are two types of sensors for remote sensing. One is the natural sun that is providing energy, and we are receiving the reflected energy from sun. This is called as passive sensors. And most of the remote sensing or the popular remote sensing happens here. It is called as the optical remote sensing. But there are other different types of sensors which are also called as active sensors that emits itself radiation towards Earth and towards Earth for the target to be investigated. And that the reflected radiation is again captured by the sensors. And these types of sensors are called as active sensors, which is a LIDAR, radar, synthetic aperture radars, and etc. The advantages of active sensors is that you can use it in the nighttime also because the source of energy here is the sensor itself. They emit radiation and they catch the radiation, reflected radiation back. It can be used in also during the cloudy days when optical remote sensing doesn't work because of the clouds. The reflected rays are not completely reaching to the sensors. So the active sensors have the capability to penetrate the clouds or to work in the night time. So we can use it during those time also. Then there are two different types of orbit where this remote sensing sensors are installed. One is geostationary orbit. That means if a satellite is placed in the equatorial plane of the Earth and it moves with the speed of Earth, then it captures the same part of the Earth every time. You can see that it captures and provides information for a specific place over the time, and it is continuously providing the information to the satellite sensor for a specific area. It is placed at on the equator around 36,000 kilometers, and it provides frequent measurements, but the spatial coverage is small. All weather and communication satellites are example of geostationary satellites. Now, what is low Earth orbit satellites? So satellites, if they are placed in the polar orbit or non-polar orbit, then they are called as the low Earth orbit satellites. They have also an elevation of between 600 to 1,000 kilometers from the Earth's surface. Now, when we place the satellites in the polar orbit and the Earth is moving equatorial, then it has the chance to cover the whole Earth with the rotation. Earth is moving like this, and the satellites are moving like this in the polar orbit. So they capture the information for the whole Earth with placing of the orbites of the satellites in the orbit. But it takes time to revisit the same place. So it takes time because it moves, and every time it captures the same area, and once it comes to the same area, it takes time. So it's a less frequent measurements, but it covers large global coverage. These are also called as sun synchronous orbit, because for the same period, so for the same local time each day, the satellites revisit the same place. So every time for the same period of time for a specific area, it passes through the satellites. Examples are Landsat and MODIS satellites. So these are the example of how you can see this is always capturing information for one place, and it is capturing information for the whole globe. There are several satellites in the orbit, and they are providing information throughout. Now, what is the product of remote sensing? The product of remote sensing is the digital images. And if you see the digital images, that there are pixels that has information about the Earth surface. So the pixels are the smallest unit of an image that has the information about a particular area. For a piece of land, they have the information about that. So the reflection, what is reflecting from the Earth surface, is recorded in the pixel. You can also see whenever you see a photo, it's also like digital images. When you zoom it, you will see the pixels. So this pixel is the information about the object from the piece of land in the form of reflection. Each pixel is associated with a digital number or brightness value. An object reflecting more energy records a higher number for itself on the digital image, and vice versa. So if the reflection from the ground surface is by a sand reflects more, so the number here will be more in digital. The digital number will be more in the digital images. And if the reflection is from the water, water absorbs most of the radiation, so the reflection will be less. And the less reflection is also reflected in the digital images. So this is the way the digital images are formed. Now, when we talked about digital images or satellite imageries, there are four characteristics of any digital image. And they are spatial resolution, temporal resolution, radiometric resolution, and spectral resolution. So they are the four characteristics of any satellite imageries. Spatial resolution is the smallest possible spatial extent measurement. So it is about the pixel size. Size of the smallest possible particles that can be detected in this. So you can see that if we have several pixels, small pixels, then the level of information will be more. And if we have a big pixel size, then the level of information will be less. because this pixel represents the average reflection from a piece of land. So if we have a bigger pixel size, like this, let me show you. So if you have a bigger pixel, it covers for a big reason only one value, and the one value is the dominant feature from that land. So the level of information recorded here will be coarser, will be less. But if we have a high spatial resolution, then we have small pixel size, and this small pixel is representing the corresponding ground area. So the information from the from a small piece of land, the information is captured, and that's why it has more information spatially. So you can see that if a satellite has a high spatial resolution, 0.5 meter by 0.5 meter, you can see the objects in that. If you decrease if the resolution will be lower, if you if you increase the size of the pixel, then the level of information will be decreased. So you see, if you go for 5 meter by 5 meter resolution images, the pixel, then the objects are not clearly visible. If you go more, then objects are even not clear. And then here you cannot even distinguish the different types of objects. So it all depends on the spatial resolution. So if we say that Lancet, suppose is a satellite image from Lancet, has a resolution of 30 meters, which means that the object greater than 30 meter in dimension will be visible in the images. But if it is less than that, we have less chances of identifying that object in the pixel. The reflection from that object is not clearly visible in the pixel because of the spatial resolution of satellite images. Now, what is the temporal resolution? The temporal resolution is about how often satellite is capturing information for the same area. So the revisit time period of satellite to acquire the information of a specific location. For MODIS, it's every 1 to 2 days, and for Lancet, it takes 16 days, around 16 days to reach the same area. So you will get images for an area after every 16 days with Lancet, but with MODIS, you can get information in daily basis. So it all depends. Then if you want to work with forest monitoring and things like that, Lancet is good because in 16 days things will not change, so you can go with that. But if you want to go for flood monitoring and things like that, you need MODIS data because they have spatial coverage. You will get daily information about a specific piece of land. Also, if you see the geostationary satellites, because they are capturing for the same area every time, so the temporal resolution is quite high. You see, you get information between every 15 minutes to 1 hour. Now, there is another characteristic of any satellite imagery is our radiometric resolution, which is the numerical range of the brightness value that records the spectral response for a pixel. It is its ability. It is determined by the bit level of specific sensors to acquire the reflected energy. So it's the ability of the satellite images to capture the information for the different reflections from an object and to put it in different space. So if you have more space for an image, you have more chances to store more variations in the reflected energy. It is calculated as 2 to the power n. So if it is a 2-bit images, it has 4 possibility to store the information about an object, that is between 0 to 3. If it is 4-bit, then it's between 0 to 15. So it says you have 16 possibilities to distinguish this object in the reflection range. You have the possibility. Most of the satellite imageries have 12-bit level data, so they have between 0 to 4095 different levels of storing the reflected energy. It also determines the clarity of the object, and also better the radiometric resolution, then you need more space for storing the radiometric energy it will increase the quality of the image, but it also make it heavy. So image will become heavy if you have more bit information, more bit images. So we have to see what will be the best level. So it is determined that the 12-bit level for most of now satellite optical images are of 12-bit bit size. Now coming to the spectral resolution. What is a spectral resolution? So different objects reflects different amount of energy in different wavelength of electromagnetic radiation, and that forms the spatial unique signature of that object that is useful for differentiating the objects. So suppose an object is reflecting more in this infrared rays differently than the other object, and if we have the capability to store or to identify the reflection in this range, then we can discriminate between the different objects. And it is determined by the spectral resolution of satellite images. So if I say that an image Landsat 5/7 thematic mapper has 7 bands, which means the Landsat images are considering the electromagnetic radiation in 7 parts. So they are taking information for one part and put it in as a form of band 1, and then the other in band 2. So you see that the wavelength of range between 0.45 to 52 is captured and considered as band 1. Band 2 is here 0.52 to 0.60 wavelength of light is captured. Band 3 is a sensor that captures the red region of electromagnetic spectrum. Band 4 is near infrared. Band 5 is short wave infrared. Band 6 is thermal infrared and short wave infrared. So the capability of Landsat 5 thematic mapper is to record the information reflected energy between 0.45 to 2.35, and they distinguish this information in 7 bands. So at the same time, when satellite is passing for an object, they have 7 sensors for recording specific wavelength of light, and when we use this 7 information in different wavelengths of light to identify the object. So spectral resolution is the ability of sensors to define fine wavelength of 5 wavelength intervals. The finer the spectral resolution, the narrower the wavelength range for a particular channel or band, and more information is observed. So you have the possibility to distinguish the object better. Most of the remote sensing images are multispectral, that is using more than one band. Fine details for vegetation types or rock types classification can be possible by more number of bands. So you see, if you see that if an image is stored in one band between 0.4 to 0.7 micrometer, it can only record the reflection, the average reflection between this range, and it's determined by one band. But if we have 3 sensors installed for the same acquisition of data between 0.4 to 0.7, and if we modify it between 0.4 to 0.5, one sensor is sensitive to capture the information between this range, and between 0.5 to 0.6, the second sensor take information, the reflection, and 0.6 to 0.7, a third sensor. Then we have 3 sensors and we have 3 bands for the same area, and we have more information because we see the reflection in this range. Similarly, if we even make it more finer, we make it 6 suppose bands, then we have more ability to record the information within the fine wavelength of light, and we have more information because we have this sensor sensitive between this. They reflect, they take the reflection only in this range, and they make 6 different bands with 6 different more information. So finer the spectral resolution, more is the number of bands. Spectral signature. So each object on Earth's surface has a particular spectral signature, like a signature by everybody has a different signature. Same like that, every object is reflecting differently. and they have a special spectral signature that can be detected by the satellite imageries. So you can see that soil is reflecting more in different wavelength of light, and then you see if you know the reflection, spectral reflection of soil, you can easily identify it in the satellite images. Also for the healthy vegetation and clear water that first reflect and then it absorbs most of the light till 0.8 micrometer. So if we have the possibility to have information in fine wavelength of light, we know the reflection in fine wavelength of light, we can identify between different objects. For specific classes like vegetation types, rock types falls in much finer wavelength range, and hence finer spatial resolution is required. So if you want to distinguish between different land use types, then it is also possible with a band with something like Landsat or Modis with bands by number of bands between 12 to 36. But if you want to distinguish between different rock types and with different vegetation types, then you need even more number of bands because they reflect quite finely in different wavelength of light. So between the vegetation or between the rock types, you need hyperspectral remote sensing. More number of bands are required for that. So you can see more bands, more detailed information. You can see that if you have a more number of bands and more information, you can differentiate between different types of crops. You can see here also different types of vegetation have different reflection, and with a high resolution spectral resolution, you can have possibility to differentiate between different crop types. You can see different rock types. So you see the different reflections, and within a small wavelength of light, you see the different reflections, and that is possible to record by more number of bands. Now, I will show you this the different comparison of a spectra for alunite rock from 4 different sensors. So if you see Landsat TM with 7 bands or with 6 bands, you see that the reflection recorded is like this. But the actual laboratory reflection is with the alunite rock is like this green color, and with Modis with around 36 bands, you can see it's also not possible to differentiate or to get the reflection from the alunite rock. It cannot represent the reflection. But with the NASA AVIRS data, that is an hyperspectral data with 224 spectral bands, you can see it is quite closely matching with the reflection, the actual reflection from the rock. So now the question is why vegetation appears green? What is the reason? The reason is the chlorophyll in the vegetation. They absorb most of the blue and red wavelengths of light, and they reflect green and infrared wavelength of light. And because they reflect green and infrared wavelength, and our human eye has the capability to see only green light, that's why the plants appear green. Though plants also reflect very good in infrared wavelength of light. So if you want to check the health of a vegetation using remote sensing, the one such famous index is normalized difference vegetation index, NDVI, which is about you take a band in near infrared, subtract with the red wavelength of light, and divide it by near infrared plus red wavelength of light, and this will give you a measure of health of vegetation. The value of NDVI is ranges between -1 to +1. So high NDVI value indicates healthier vegetation, and low NDVI value indicates less or no vegetation. And how you calculate it, you can see that if a plant is healthy, Let me take this arrow. I'm always, yeah. So you see this, if a plant is healthy, it is reflecting more infrared light and absorbing more um, uh, and absorbing more light, red light. So once the plant is not healthy because of water stress or because of disease or because of whatever reason, then the chlorophyll content get decreased and it is now reflecting less infrared radiation and taking more visible. So if you subtract it, and you will find the NDVI value, and you can say that NDVI is, if it is decreasing, it shows that the plants are not healthy. And if the NDVI value is higher, then it shows that the plant is healthy. So you can have an indication about the plant health using NDVI. Now, there are two concepts. One is true color image and one is false color image. The true color image is when we see an object. The object is like band 1, we have the reflection in blue wavelength of light. Band 2 have a reflection in green, and band 3 has a reflection in red region of light. So if you give the right color to them, then it is called true color image. And here then the vegetation appears green because we are providing the true colors. But now, as we know that infrared radiation for vegetation, because infrared radiation is reflecting quite good for the vegetations and has quite good information about the vegetation. So if we give um, uh, red light to near infrared, and if we shift the light color, if we shift the color, and if we give near infrared as red, and then green, red as green, and the blue as green light, green wavelength of light, then you will have a false color composite. By using this, you give color to near infrared, and you can visualize the information that is captured in near infrared spectrum of light. So you can now get more information about the plant or about the vegetation. Now, similar to NDVI, there are different indices for water. So this is normalized difference water index, and that is used for mapping water bodies and changes related to the contents of water bodies. So it can be useful with the flood monitoring. It is calculated as the green band minus near infrared, and divided by green plus near infrared. Also, we have the possibility to calculate using the same NDVI index, but with different bands, have the possibility to measure the changes in the water content of leaves. So using this indices, you can also have possibility for drought monitoring. So if we take near infrared and subtract it with short wave infrared, divide it by near infrared, and plus shortwave infrared, then you get a value. And the value of the NDWI is ranging between -1 to +1. And same like NDVI, if the value of NDWI is higher, it indicates water bodies. So usually if it is larger than 0.5, it's a water body. Vegetation has much less smaller values, which result in distinguish vegetation from water body easier. Build-up area has also positive values between 0 to 0.2. So you have a possibility to differentiate between water bodies. You have the possibility to map the water bodies using normalized difference water index. Now, with remote sensing, there is always a trade-off, because if a satellite is taking information about the Earth's surface in fine detail, it needs time. It moves and it takes time to cover the Earth's surface. It also depends on the swath of the satellite. So if the satellite is taking a bigger area and taking a fine detail about the area, it moves and it takes time to reach to the same place again. So if a satellite imagery is having higher resolution, higher spatial resolution, then the temporal resolution will be less. Um, and it's always a trade-off between different scenarios with the different high spectral, spatial, temporal, and radiometric resolution at the same time. So if you see the example of Landsat, which has a spatial resolution of 30 meter, but temporal resolution is of 16 days. Similarly, MODIS with a coarse spatial resolution but fine temporal resolution of 1 to 2 days. Therefore, it is necessary to find compromises between different resolution according to individual application, or to utilize alternative method of data acquisition. So now that is all about the remote sensing. Now, what is a geographical information system, GIS? They both are different terms. It's not one term, but people often take remote sensing and GIS as the same term. GIS is basically a computer system designed to capture, store, manipulate, update, analyze, and manage different types of spatial data that is acquired using remote sensing. So remote sensing is about acquisition of data, acquisition of spatial data, and GIS is complementary. GIS is about analyzing the remote sensing or the spatial data and get the results and show the results in the form of maps. So GIS, there are two different type of GIS data. One is vector data that represents the real world in the form of point, line, and polygons. So you see the river, if we disguise it in the form of line, we can disguise the river in the form of line. For the settlement, we can disguise it as a polygon. And if there is a landmark or hospital, we can differentiate, or we can assign it with the point. And that is called a vector data that has a georeference data that has a coordinates about the locations. Now, the other type of data is raster data. So all the satellite images are raster data that has a pixel, and the pixel stores information as such, like remote sensing satellite data. So these are called as raster data. Now, there are different types of remote sensing satellite data that I have listed here, and you can have a look on the different types of important remote sensing data. So Landsat 7 has a spatial resolution 15 meters, 30 meters, and 16 meters. So different bands have different resolution. The one with the visible region is with the 30-meter resolution. Temporal is 16, and number of spectral bands are 8. Landsat 8, you can see the different spatial resolution. 100 is the resolution. 100 meters actually is the resolution for thermal bands. Has a temporal resolution of 16, but the visible region is captured in 30-meter spatial resolution. So if you want to go for land use mapping, the resolution of the Landsat 8 and Landsat 7 is 30 meters. They provide information in 30 meters. MODIS has a resolution, daily resolution, and has 36 spectral bands. Sentinel 2A and 2B are now popularly used. It's from European Union, and now they are freely available and having quite good resolution of 10 meters. So you have a 10-meter resolution data. Temporal resolution is of 5 days, and spectral resolution is 12. So these 4 are freely available. You can download it for your use. Whereas you can also find high resolution, spatial resolution data from QuickBird, Equinox, and Spot, and there are commercial data sets. So you have to pay if you want to use this data. Now I will show you different links to download remote sensing data, and I'm going to show you only those remote sensing data that are freely available. So the first one is the Google Earth Engine. So if you click to the link, you will get a website where you can download, where you can have a possibility to see different data, satellite imagery data sets. And the good thing about this website is that you don't need to download the data, but you can work with the data, analyze the data, and you can save the work. And you can then download the work which you analyze on the website. So because the data is heavy and you don't need to carry this data, you don't need to download the whole data. You can work with the data online and you can save it, and then you can download the results. So it's very user friendly and convenient tool and ready to use data. You'll find Lancet data sets over 40 years and Sentinel 1 and 2 MODIS, different data set you will see. You can just explore this the site afterwards. Then there are other websites where you can download data, when you can download Lancet data and then use on your own computer and analyze it for different applications. So it's a famous one is USGS Earth Explorer. You can go on this site and you can download Lancet data for 40 years and Aster data and different data models also you will find it here. Then comes the Sentinel mission from European Space Agency. Recently, they has opened the platform to download the data in very high resolution of 10 meters. So these data are freely available, and you can have access to this data. You can go to the website and you can see where to download the data. Then you have also possibility to download data from NOAA class, and then there are other several listed platforms from where you can download data. Here is a global land cover facility. So you can download directly the land cover. The land cover is mapped by the agency and for the whole world, and you have the possibility to download the data from this with this link. Then you have also possibility to test the high resolution data, which are basically commercially in use, but they also provide some data for the students or for the researchers to test and to learn. So you have the possibility also to check through this three websites and get more information about where to download high resolution data. So they are the sample data, so you have the possibility to check on that and see which one is. Now, there is also possibility to download near real-time data for disaster risk management, because during the time of disaster, they provide the remote sensing images just within 3 hours from the observation, whereas in actual case, it takes 8 to 40 hours to provide the data on the server. So in case of emergency, you have data in 3 hours from this website. You have the possibility. In general, the other data is processed data that needs time and takes 8 to 40 hours for their availability on the website. You have other different links from where you can have data, real-time data in case of rapid response, in case of hazards and disasters. You can go to this website and can download the data for your area, and you can just check what is type of disaster and how you can provide management issues for that. So you have the possibility to look on that websites and get the information. Now, I will talk about how remote sensing is useful for acquiring the data, the hydrological parameters, different hydrological parameters, and the important ones are precipitation, soil moisture, and evapotranspiration. So using remote sensing, you can have the data for precipitation, soil moisture, evapotranspiration, and these data are freely available to download. So let's start with precipitation, which is the major component of water cycle, and The first famous mission was Tropical Rainfall Measurement Mission (TRMM) that was providing data between 1997 to April 2015, and it covers the region. It covers only for the tropics, between tropics and subtropic. So it is covering, so you can see that Africa is covered in the tropics and subtropics, and is providing data for only that. So it's not a global product, but it's for the tropical and subtropical, which covers most of the land areas. So it is providing information, and then different types of sensors are installed. I'm not going in detail. You will find more information on this link. So now, in 2015, this TRM mission was finished. Then the successor to TRMM is a Global Precipitation Measurement products, that is by NASA and Japanese Aerospace Exploration Agency. That started providing data from February 27, 2014, and the data is available from that time to present now. So this is the latest satellite product for rainfall. Spatial resolution varies, but the temporal resolution is 2 to 3 hours. So the advantages of GPM over TRMM is that it covers the whole globe. It also detects the falling snow. It measures the light rain. It provides quantitative estimates of microphysical properties of precipitation particles. So you can get more information about GPM with this link. And there are the links mentioned here where you can find this TRMM and GPM precipitation data for download. Now, the other product is TRMM multi-satellite precipitation analysis. That is a combination of TRMM products and other satellite observations, so a combination of different sources to produce this TMPA. It provides a temporal resolution of 3 hours, so you will get data at every 3 hours with a spatial resolution of 0.25 degree by 2.25 degree. And this also spatial coverage is global, and it's still in existence, so you will get the real-time data is now available from this product. And this TMPA is used for flood monitoring and environmental application, and different models use this product for flood monitoring. Now the latest and the latest with the highest temporal resolution rainfall data is available via integrated multi-satellite retrievals for GPM. In short, it's IMUG. So it is a combination of GPM, the latest mission, with the GPM constellation of satellites to yield high spatial and temporal precipitation estimates. So you get the information at every 30 minutes. So it's a quite high temporal resolution, and a spatial resolution of 0.1 degree by 0.1 degree. It also captures the whole world, so get the data. These are the links to get the data. Now there are several products by different providers, so you can have a look on this different products. With the remote sensing satellite images, you will find different products that estimates remote sensing data. You will also find the historical rainfall data such that back to 1901 based on the global GAUSS measurements, and these are the interpolated data sets for any part of the world, and you can click and you can get the data of your area for historical databases that back to 1901. Now coming to other hydrological variables, it says another product is a modern era retrospective analysis for research and application, and that is MERA data, and they have providing information from 1979 to present, and they provide information by integrating remote sensing and also the ground measurements. So they have a integrated product, and they have a special focus on hydrological cycle, and the spatial resolution is in 0.5 by 0.5 degree grid. So it provides information on rainfall, temperature, wind, relative humidity, leaf area index, total soil profile, soil wetness, and soil temperature, transpiration, etc. It's also providing for entire globe, and you can have a possibility to download the data from this link. Now we have used this metadata for rainfall for Central Asia, and where we found that the data captured by this metadata is quite good. It's matching quite good with the compared to the observed data for one of the stations in Central Asia. Then there are other different websites where you will get different types of data. The links are mentioned here. You can check, and you can check from when to when the information is available, and what type of information is available, what type of data is available. So you can go and click on this links after the class. For soil moisture, the product is soil moisture ocean salinity moss. That is by European Space Agency, and the data was only available for 3 years, because then afterwards the mission was not collecting information. So it's only for the period 2009 to 2012. It also provides information about the soil moisture with a spatial resolution of 25 to 50 kilometers with the 3 days temporal resolution. You can have a look on the link for more details. And now the latest one is soil moisture active passive by NASA, which was launched in January 31st, 2015. And it has a spatial resolution of 9 kilometers with a temporal resolution of 2 to 3 days. And the data, available data with the validated products are available from July 2016. And it is currently providing the data. So you have a look on the soil moisture active passive products. The limitation is that remote sensing cannot look deep in the ground. So with the microwave, it can only have possibility to see the soil moisture in 5 centimeters of depth. But using indirect measurements with the running models, you can also have access to soil moisture estimates indirect way with the 1 meter count, 1 meter deep. You will find more information on this link. SNAP data. So you have now evapotranspiration. What is it? It is a process of by which there is a summative loss of water from the soil surface in the form of evaporation, and from vegetation growing on it from the form of transpiration. So it's a sum of transpiration and evaporation from an area, and it is considered as the second largest components of terrestrial water balance after precipitation. It is highly variable in both space and time. And the different factors that affects ET is the solar radiation, temperature, wind speed, atmospheric vapor pressure, and soil moisture. It is very important in irrigation, in planning irrigation schemes, because it can provide you the water demand by the crops, and you can see what is the water supply to the scheme, and then you can have a irrigation scheduling in an area. Now, how ET is estimated? It is basically estimated at field scale with point station estimation. The famous one is Penman-Montet method, and also with the lysimeter and eddy coherence. But these are the point scale measurements, so they provide information for an area, but not providing information for the spatial distribution. So you take the information from point scale, and then you interpolate it for the area. Using remote sensing, it's also possible to estimate evapotranspiration, and the different methods are surface energy balance algorithm for land, that is Spatial algorithm, that is based on remote sensing to estimate evapotranspiration, spatially, like in the grid form. So you have the information for every grid, and you are considering or capturing the spatial variability in evapotranspiration using remote sensing. And there are different other methods like mapping evapotranspiration at high resolution with internalized calibration, that is metric, and also with the new surface energy balance system SIPs. So I will not go in detail, but it's about latent heat flux is basically reflected as evapotranspiration, and it is based on the energy balance. And we have the possibility to capture the information like soil heat flux using vegetation indices and surface albedo. So there are different satellite products that is available that estimates evapotranspiration, and you have the possibility to download these products as well and to check its applicability for your area. So one such product is also MODIS Global Evapotranspiration Project. MODIS 16A2 product with a spatial resolution of 500 meters with a temporal resolution of 8 days. So you can have the possibility if you want to download and if you want to have an estimate of evapotranspiration, especially for your area of interest. But you have also the possibility to design or to estimate remote sensing based evapotranspiration at 30-meter resolution using Landsat by utilizing the algorithms like Spatial and metric. So if you want to do it by yourself, you have the possibility to go with the high resolution, or you can use the available product and in coarse resolution for your application. There are also several work right now going on to downscale the coarse resolution MODIS products of 500 meters. So using different techniques in using multi-data fusion approach and also Alexi and dis-Alexi approaches, scientists are now downscaling the MODIS products with 500-meter resolution to local scale for their use in the scale of maybe Landsat. So you can also check the different downscaling approaches to downscale the data. Now, it's also possible to monitor surface water quality using remote sensing data. What is possible till now is to go for estimating of physical properties, that is color, temperature, turbidity, total suspended matter, in chemical salinity, and for biological properties we can estimate algal bloom or chlorophyll A and dissolved organic carbon. So how does it work? As I said that each object has its specific spatial signature, and within the water, using satellite imageries, the reflected or emitted surface reflection measured from the water bodies that talks about the different water constituents. Using the top of atmospheric correction radiance values, we have the possibility to determine the water quality, different water quality parameters. So the beauty is that we have the ground measurements, we have the water quality for point location. Now we use this point location, we have satellite images with every point has a value with the pixel value. So we have complete more information for the whole area in pixel. In every pixel we have a value. Now if we have an algorithm where we can correlate with the space, the field observed value with the satellite indices, then we can map for the whole area. So we can upscale for the whole area using just a field measure, a few values from the ground. And then that is quite effective if we can able to make a correlation or to make an algorithm between field observed value with the satellite products, and then we can have a possibility to monitor it. Now the good thing is once the algorithm is developed, then it is providing information in continuous time steps. So with the field measurements, you have the possibility only to go and take observation for one time, and that is also time consuming and costly affair. So if you have remote sensing images and if you have a correlation already existed between that, then you have the possibility to get information at regular interval of time without any cost. So that can be nice, but there are several constraints also in having this, because the cloud coverage is hindering the information, and you also need a top of atmospheric correction for that, and also you need sufficient in good numbers the water quality measurements from the ground for correlation with satellite images and algorithm development. So you can see how you can map water quality using remote sensing. Now, one thing that I want to mention is that the important thing is that the water bodies that we are mapping should be a closed water body and not a moving water body like rivers, because rivers, once you take an information, then it changes if it is a moving water. But with the closed water bodies, you have more possibility of accurate water quality monitoring. Now, I will show you the different applications of remote sensing in GIS in water resource management. Using remote sensing, this GRACE recovery and climate experiment, that is a joint project of NASA and DLR, German Space Agency, based on the Earth's gravity field. What happens here is that two satellites are moving along the Earth's surface, and if there is a change in total terrestrial water storage, then it reflected in the gravity, and with the change in the gravity, there is a change in reflected in the movement of these two satellites, and this change is then translated to measure the change in total terrestrial water storage. So it's a very innovative approach of determining the groundwater storage, how the groundwater storage is changing. This mission was between 2002 to 2015, so we have the data for between that period, and then the follow-up has recently started in May 2018. So there is another mission now in 2018 with more improvement in providing the data. The problem is the spatial resolution is quite coarse with the GRACE measurements. It is very coarse and depends on the signal. So if you wanted to go with the state level, then it's not possible. You have to go for a very big area, for a continent or for a country level or for a big basin level, then only it will work. Otherwise, if you want to do it for some small scale studies, it's not useful. The temporal resolution is also monthly time step, so but it covers for the entire globe. Let's see for what is new features in the new one, in the new follow-up missions that started in May 2018. So using this application of GRACE, you have several applications for like drought monitoring, groundwater depletion, seasonal snow load, stream flow forecasting, transboundary water resource sharing. Then you see that using this GRACE mission, the different groundwater original mass flow was estimated for different part of the world. You see that the groundwater loss was estimated in India, in the northwestern part of India. You saw that we saw that within the 6 years, and there is a loss of 109 cubic kilometer of water from the aquifers of this region, showing an alarming situation for the decision makers to act on this issue, because it's quite a lot and quite unsustainable overexploitation of water resources is in this area, and that is found by the GRACE mission. It was also compared with the groundwater observation in Illinois, and it was found that it quite fits with the observed data, this estimates from the GRACE. And we could have think about the other application is in flood inundation and mapping and monitoring. So you can have a possibility to look on the floods with remote sensing. You can this is the image from 18 April 2019 before flood for the Niger Niamey area, the river Niger. You can see that this is the normal flow of the river, and during the flood event, if you see on 29th August 2012, the water is now spread in the settlement areas. Using remote sensing and GIS, you have the possibility to assess the areas that are flooded, the extent of water bodies that are flooded, the reason. You have the possibility to calculate it. You can also find the different damages to the infrastructure because you have the GIS layers for this settlement and other infrastructure. You can also see the roads that are destroyed in the flooding events, and you can then look for the plan for evacuation, that which road can be considered during the flood event to rescue people. So it can be only possible using the satellite images and having a spatial view of the flooded water in the region. So this is one of the application that is used. You can also have the possibility for agriculture drought assessment and monitoring using remote sensing. And as I said, that in NDWI and NDVI are the vegetation indices that indicates about the health of vegetation. Other several vegetation indices are available, that is vegetation temperature condition index and VHI and different others. That was quite useful in determining the moisture status of soil and also vegetation, and indicate about the drought and early warning systems in our area. You can have also possibility with the soil moisture, and you can have estimates of soil moisture and evapotranspiration using remote sensing techniques. Now that you have also possibility for irrigation infrastructure and potential using Cartosat satellite images. You can see the different schemes here in the area. So you can have possibility to see whether in the canal network, whether a miner is connected with the distributary, or if the miner has a length, whether it is matching with the one which is proposed. So you can have access, you can measure this length of. So you can also have possibility to see what is connected, what is not connected. In the satellite images, you can clearly see that the miner is not connected with the distributary, and that is a problem. So you can act accordingly. So water supply and demand analysis is possible. Groundwater prospect mapping is possible. There are several applications, so I cannot go more in detail because of time issues. Mapping of natural bodies and sites suitable for making dams and percolation plan using remote sensing images. And also an important application is assessment of reservoirs and sedimentation or water body sedimentation using remote sensing. Now I will come to the practical part. As I see that we don't have much time, it's only 15 minutes left, so I can quickly take a look on show you the different steps for downloading remote sensing satellite data for rainfall. So maybe I will not do the practical. I just show you that with this link you can reach to the website, and then you have the possibility to download different types of remote sensing rainfall data. Then you can have a possibility to download, and you have to register it, and then you have to download. Then once you will choose all the specification, then you will get a link for this data. Once you have the link, you take that link, you rename it myfile.txt and put it in a folder, maybe C folder, and then you make a folder in C and make it something like any name, rainfall. Then you also download GGet software from this link. You put all this information in C drive under rainfall folder. Then you start your CMD command. You make a cookies with this command, and then you put this command. Then once you put it, they ask for your username. Mine is Navneet. I put it already here, and then they ask for your password. Once you put the password, the downloading will start. The beauty of this application is it's not only one time, because if you want to download the images or rainfall estimates, satellite data, then you have to click every time one by one. But suppose if you have several data for 3 hourly data and for several years, it's not possible to click one by one and download it. So this is quite useful to, this approach is quite useful to download in bulk. So yeah, it is here. You can have a look on that and can do. Similarly, with the downloading of images from the website Earth Explorer, you can have a possibility to first look for the Java is installed or not. And after looking Java is installed, then you can go for Earth Explorer and then register it here, and then you have the possibility to choose. Then you choose the name of the place where you want to download. Then I put Clemson in Algeria, it's showing here. Then I choose for the data set, and if I click for the data set, I have different data sets, and then I put the time period from where to when I need the data. Then I click for Landsat 8 images, and then you have several opportunity for download. And then you click this one of this one, then you can download it. Then it is showing the different specification of that image, and then you have the possibility to download, and then it shows that your order has considered, and then a mail will come when it will processed, and then you have the possibility to download the data. And this is about now it's about the digital elevation model. So you know that SRTM DEM is available, which shows about the elevation of an area with the 30-meter and 90-meter resolution, and also AstroDEMs are available with the 30-meter resolution. And you have the website here to go and download the data. So I just wanted to show you the websites and way. Then you have also possibility to look for the flood monitoring and management system. So what is possible? There are three possibilities. One, you can have a look on the real-time flood monitoring, then flood intonation modeling during and after the flood event, and flood forecasting. So you will find the different wave monitoring tools that uses remote sensing observation for flood monitoring. One is global flood monitoring system. The link is here. You can have a look more in detail after this lecture. You also have infer flooding conditions by using satellite derived precipitation, and also flood intonation mapping, detect flood, water, and previously dry land surfaces by using MODIS and Dartmouth flood observatory. The link is here. So with all this, I would like to finish my presentation. And now the floor is open for questions and discussion. So now you can stop it here now. Yeah. Anna and Yannick, are you there?
Thank you very much, Navneet, for your really precise and interesting presentation.
Thank you.
So I think we have about 10 minutes left for questions from your side. So feel free to ask whatever question you have come up with.
Yeah, I have a question about the soil moisture that I mentioned, that the current map information for soil moisture active passive product, it can penetrate only till 5 centimeters. The possibility is to penetrate only till 5 centimeters, but they use the models. There are different models developed, and with the indirect estimates, it can go till 1 meter. So you have the information, direct information for 5 centimeters, but it is also possible to get until 1 meter. I think yes, you can get my presentation.
Thank you, Navneet, for this offer. We will upload it then together with the recording.
Yeah. Let me carry on that. The idea here is to inform you about different remote sensing products because when you start your work, you are always have problem with the data. You are always looking for data to start with your work. But there are several websites and servers where the data is available. You can use the data directly without paying, or it's free of cost and estimated by different remote sensors. So that are quite useful for any work, for any hydrological modeling, or for any spatial planning applications. The only thing is, whenever you use remote sensing data, you should be very careful because for some area they are very good in performance, but at several area the products are not good. So you have to validate it with the ground observed data before you use it. And there are different products, so you have to make a comparison which one might work for your area. That is also very important. So um, yeah, there is a question that is there any ethical regulation that govern the use of spaceship device? I don't Yeah, there are different organizations that are working on, like one is UNUSA, that is United Nations Outer Space Affairs, that is looking for governing the different regulation for space applications. So, um, but the data, remote sensing data, if it is freely available, it is freely available. You just have to click that you get the terms and condition for using the data, and you can use it freely. So. I would Ibrahim has asked that I would like to know where the difference between the station data and the sensor data comes from. There are two quite different data. Observed data is from the ground, what you take, and remote sensing is the reflection of the object that is recorded. So the information type is quite different. And generally, when you use a remote sensing product, you need the ground information to validate the remote sensing products. And um, I think you got your answer. Isaac is asking that is Africa not vulnerable to those spaceships to be used as spying mechanism of the continent? Yeah, it may, most of the remote sensing data is about getting information. So yes, I mean, it could be vulnerable, but this data is available, and it is also useful for several applications. So it depends how it is used. So I can't say that it is also something for a spying mechanism, uh, but the data is available throughout the world, and this data is for different application, for different development purposes as well. I mean, that is the important purpose of having remote sensing satellite data, and it depends on how one can use it. Uh, yes, there are websites available that gives information on discharge measurement. Maybe let me check it. There are global run for database by Germany that you can have a look on that. Maybe I will type it here. You can explore this website and have a look on the different run of data that is available throughout the world on this website. Hi, Alfred. That there are different softwares available for processing this different images. Um, uh, DAS imaging is one of a software that is quite good with the remote sensing data, and there are several others. So, and the GIS applications is always remote sensing, or for GIS application especially is ArcGIS, and also QGIS that is freely available. So people are using those software for GIS applications. Soil moisture estimates are available with the remote sensing. You can download this information, but the resolution, if you have seen, the resolution is quite big, quite coarse resolution with the spatial 9 kilometers. So with farmland, I don't know how it can be applicable, but there are different techniques now people are using to downscale the soil moisture estimates, and you have to look for the different techniques, and there are different softwares that are used to downscale multi-data fusion approaches, and there are several information. You have to look on that how different mechanism of downscaling, and that's why you can only use land soil moisture estimate for a farm scale, because with the information that is available is quite coarse right now with remote sensing. What do you mean by land use simulation model, Alfred? Can you tell a bit more clear about that?
Thank you, Nafid, for this information. Are there further questions from your side?
There are several models for land use simulation, Fred, so I cannot say which one will work exactly for your purpose. You have to look for the different features and your basic application, what is basic requirement for you, which land use class you want to simulate, which land use types you want to simulate. So there is no ready-made answer for this question. So you have to check different models. There are several models existing. So um, how are that if you want to model evapotranspiration, this then or soil moisture, then you can either go with the remote sensing derived products that are freely available, but they are of course resolution. So if you want to estimate by yourself, if suppose evapotranspiration, then you need a basic software of remote sensing. You have to look on the Sebal methodology. You will find this. There's different steps and the user manual about Sebal. If you type Sebal and user manual, then you will get the manual and you will get the steps how to proceed. And these steps can be proceed in any basic remote sensing software such as ADA. So it's not a specific software for that, but you have to see what are the components or what are the steps that can be useful for that can be processed in any other any basic software. So yes, it is possible to find the flood risk areas. It's using remote sensing data. Yes, of course. You have the possibility to get elevation for the area. You have the possibility to see the river side, and then you can estimate what are the areas for risk. How, what is your question? You mentioned how, what is your question? Yes, Pauline, you will get the presentation. Uh, you will get the data on, if you see my presentation, I also mentioned that it's a SRTM DEM and it's a Aster DEM that has data for elevation. So you can download the data, elevation data for your area. Free of cost, that is freely available data. Nowadays, there is also LS Pulse, that is a high resolution elevation data with 15-meter resolution. And I have also not used, but I know that the German Space Agency DLR has a TerraSAR-X data that is about the elevation of the area. It's a recent product. You can also explore on that different. But SRTM is a data that is used for the hydrological purposes for many years. So maybe I can give you the link for that to download. I was supposed to show you on that, but the time does not permit. I just mentioned it here, so maybe you can have a look on this website for. Hi, Pauline. Then I mentioned that this remote sensing data is available for the whole world. So you will find the data on the respective websites. I mentioned several websites. So once you have the presentation, you can try with this different links and explore the data. If you're concerned about distal elevation model, I mentioned the above two links where you can find the elevation data. But if you want to have land use maps or um, then you can go for USGS website for um, downloading the data. Maybe I will give you for land use. You can no, for the satellite images. For satellite images, can have mention several links for downloading the data. Any other questions? You can find a full literature on flood risk management using remote sensing data. So what we need is generally the rainfall. If we have the information on that, elevation, also we can see for the settlement area, we have different layers of settlement. So if we impose the settlement layer, we have elevation data. We also have historical data about the flood events, that which areas was flooded in the past. If you have the information about that, then we can talk about the flood risk and the flood vulnerability for an area. So you can find different literature on that. First, you have to go through that literature, but the data are possible using remote sensing, and also there are different GIS layers that are available free of cost. So if you want to have this, you will get the data in public domain. So the only thing is you should know the technique, and that you will find in the different papers. Mohammed, I don't know at the moment that whether it will be further projects that has PhD component in that. Maybe yes, maybe not, but you have to check regularly, maybe. But at the moment, I don't have an answer for that, because I don't have further information what will be for the next year. You can also look for the ZAF website. We have a PhD program that is every year. So let me show you that you can apply for a PhD in ZAF. It's every 31st of August is the deadline for every year to apply for DAD scholarship. So um, you can have a look on, on, on our PhD program at ZAF. So you can have a look on that. Any further questions or? Any further questions, or shall we close this session now?
No. So yeah, no. It seems like there are. Okay, somebody is still typing. But okay, no. Just thank you. Okay, so I think we can round up the session. And thank you again, Navneet, for this really interesting presentation and for being available for questions. And
Thank you.
So, to all participants, thank you for attending, and I hope it was very interesting for you as well. So, now I think we will see again tomorrow for the feedback and the discussion of the reflective review exercise. And otherwise, yeah, have a good evening and see you then.
Okay, bye.